Hello everyone. This video will be about the solutions of Unit 2 IAL Physics of the January 2021 session. Let's begin. First 10 questions, of course, MCQs. So first question is find the units, SI base units included for power. So power is basically what? Power is work done by time. Work done is basically what? Work done is force multiplied by distance by time. Force is basically what? Force is m into a, mass into acceleration. So mass is kg, acceleration is meters per second squared, into d is meters divided by time is in seconds. So which SI base units are included? Of course, meter, kg, and seconds. In here, out of the options, we are only left with kilograms. So that's why we choose kilograms. Okay. And Newton is not a base unit because base units are basically SI units, which can either be kg for mass, meter for length, and second for time. These are the base units, so you have to make sure these are included. Number two, it's basically a combination of series and parallel resistors. So y and z are in parallel, so we have to use the parallel combination formula, which is product by sum. So product is yz divided by sum is y plus z, and because this combination is in series with x, that's why you add it with x. So x plus yz by y plus z. Then which of the following statements about ultrasound is incorrect? Is correct. So all of the ultrasound is reflected at a boundary between different tissues. Wrong. They don't all get reflected at the same boundary. They get reflected from different boundaries. Ultrasound travels faster in air than inside the body. That's wrong, because sound travels the fastest in solids, not in air. Ultrasound with a greater wavelength gives an image with high resolution. Higher wavelength means lesser energy. We know that, right? If there is lesser energy, you're not gonna be able to penetrate deep into the body. That's why high resolution is impossible. So that leaves D, which is the only correct answer. Number 4, which of the following demonstrates the photon model of light? There's only one, which is the photoelectric effect. Then number 5, this is basically core practical 8 of unit 3, finding EMF and internal resistance of a cell. So from that knowledge, we get to know that the y-intercept of the graph is actually the EMF. That's it. Then the resistance of the variable resistance R, which of the following gives the current in the cell? So of course, this is a series circuit, and in a series circuit, the current is basically the total voltage divided by the total resistance, and the total resistance is simply the addition of the resistors, which is small r plus capital R. So we get the total voltage is E, total resistance is R plus R. That's what we got. Then which of the following statements is correct? So as you can see, this is the time axis from where you can get the time period. So time period is the time taken to produce one full wave. It starts from here, ends here, so it takes 0.4 seconds, and we know frequency is 1 by time period, so 1 by 0.4, which is simply 2.5. That's the answer. And then this is about critical angle. So we know that whenever something exceeds the critical angle, whenever the angle of incidence is more than the critical angle, all of the light is reflected. So that critical angle is 42, and the light here is striking at an angle of 45 degrees. So that means it is more than 42, meaning all of the light is reflected, total internal reflection. Number 9, which of the following is correct? So lambda is h by p. This is de Broglie's equation, de Broglie's wavelength equation. H is the Planck's constant, p is the momentum of the substance of the particle in question. So the de Broglie equation, out of these you have to find the correct one. De Broglie equation is independent of the mass. Of course is wrong, because the momentum contains mass. The term p represents the mass of an electron multiplied by the speed of light. Not necessarily, it can be any particle. It's not necessarily it has to be an electron only, right? And also they're telling us that the de Broglie suggested that electrons have wave properties. Fine, it's not necessary that the electron has to have the it has to have the speed of light. Not necessary, right? The value of h depends on the particle involved. No, h is a constant. It's Planck's constant. It doesn't depend on anything. It's independent of everything. So the only correct answer is number B. Then this is about finding the currents in amperes, and the current is basically charge by time. So we have to first find the charge. So 3.1 into 10 to the power 19 electrons, they have a charge of 3.1 into 10 to the power 19 into 1.6 into 10 to the power minus 10. Why? Because each electron carries 1.6 into 10 to the power minus 10 coulomb. So 3.1 into 10 to the power 19 electrons will carry the thing in the numerator. That is the total charge of these many electrons. That's in the numerator. And since current is charged by time, charge divided by time is 30 seconds. That's the answer. Now we move on to this one. This is drift velocity. You have to find the drift velocity. So I is NAQV, N is the number of charge carriers per volume, A is the cross-sectional area, Q is the charge of each electron, and V is the drift velocity. From here, we found the drift velocity. The only thing that we had to take into consideration is the radius. It is in millimeters. You have to convert this to meters. So that's the only thing you have to be wary of. Number 12, as you can see, it's related to superposition. In A, as you can see, it's empty. Empty means there has been destructive interference or destructive superposition, and that happens because the waves are out of phase by pi radian. Pi radian means 180 degree, right? So if they are out of phase by 180 degree, that means totally out of phase. That means total cancellation. In position B, you can see it's full. It's not empty, it's full. Why? Because there has been constructive superposition, and that is only possible if there has been 360 degree in phase, superposition. Both of the waves are in phase, and they are 360 degree or 2 pi radian in phase. So that's what you have to say. Number 13 is about basic resistance. It's a series circuit, and the calculate the resistance of the LDR when the lights were off. So in a series circuit, the current is the same at all points. So current here is all the same. So if I simply find the current through the, this 5 kilo ohm resistor, that same current is flowing through the LDR as well. So from here I found the current, which is 2.38 into the power minus 4. That same current flows through the LDR as well. From that, we can find the voltage across the LDR. That's what we did. Then when the lights were switched back on, so whenever you switch the lights back on, of course, when the light intensity increases, the resistance through the LDR decreases. And if the resistance decreases, that means the voltage automatically drops, because V is equal to I into R. So if the resistance falls, the voltage also falls. So that's what I wrote here. As the voltage across the voltmeter is more now due to the increase of current, the V LDR decreases as the 1.50 volt has to be shared. So this is a series circuit, and in a series circuit, we know what? We know that in a series circuit, the voltage gets divided. So 1.50 volt, previously, a lot of it was going through the LDR, but now, because the current has increased, and this one's resistance, why did the current increase, by the way? This one's resistance fell that way. That's why. The resistance of the LDR fell, that is why the current in the circuit increased. Now, because the resistance fell, that means what? That means that the voltage would fall. That's what I wrote. Now, the voltage falls. The voltmeter is only capable of reading up to 0.01 volts. So that means because of this low resistance, the voltage of the LDR fell to such a small amount that it was even less than 0.01. That is why you couldn't read it using the voltmeter that we have, right? So that's what I wrote. As the voltage across the voltmeter is more, now due to the increase of current, the V LDR decreases as the 1.5 volt has to be shared. The PD across LDR becomes less than 0.01 volt, which is why you cannot read it. Number 14 is about energy levels in gases. So they have given us two cases. One is the electron with kinetic energy of this much interacts with this atom and causes one of the electrons of the hydrogen atom to jump from minus 13.6 up to minus 1.5. Now, point to be noted is we need the exact amount of energy as the amount which is between the two levels. So the difference between the two levels, 13.6 and 1.5, is exactly 12.1. But from here we are getting 12.3. So technically speaking, that should mean that this transition doesn't take place, but in this case we can see it is taking place. So transition requires 12.1, but we are getting 12.3. That should mean technically that the transition should not take place. It has to be exactly equal to 12.1 for the transition to take place. However, it is happening here. So the remaining 0.2, which is left out of the 12.3 out of 12.3, 12.1 goes away towards the transition, and we are left with 0.2 electron volts. That 0.2 electron volt, what it's doing is actually this 0.2 electron volt is the energy transferred to the next electron. This electron which is already transitioned, that's already transitioned, but the electron which comes next in line in the hydrogen atom, this 0.2 electron volt, this extra energy has been transmitted to that next electron in the hydrogen atom, which is about to transition next. Okay, but when it comes to the photon, the same amount of energy, 12.3 electron volt, is provided onto this atom by a photon, and nothing happens. It stays at minus 13.6. Why? Because it's not exactly equal to 12.1. It has to be exactly equal to 12.1 for the transition to take place. But since the photon cannot provide exactly 12.1, it's providing 12.3. Even though it's providing more, it doesn't matter. You have to provide the exact amount. So because it is incapable of providing the exact amount, that is why the transition doesn't take place. It will only be possible if the energy provided by the photon is exactly equal to the difference in the energy levels. That's how it works. That's what I wrote here. So number 15 is about refraction. Refraction is the bending of waves when they change medium. It happens due to the change of speed while changing the medium. In here, you have to find the refractive index of the water. So refractive index, to find the refractive index, you have to make use of this formula, Snell's law. N1 sine theta 1 is N2 sine theta 2. N1 is the refractive index of the light in medium 1. Theta 1 is the angle in medium 1. N2 is the refractive index in medium 2, and theta 2 is the angle in medium 2. So we need to find the angles first using the dimensions which we are provided with. So we use tan theta for both the water's angle and the air's angle. Once we have found the angles, we put them in this formula and we can find it. And point to be noted is the air's refractive index is always 1. It's always 1, so it's a fixed value. Refractive index of air will always be 1. It's the reference value. Number 16 is a star mark question. Whenever you have star mark questions, you have to be very, very decisive. You have to be very descriptive. You have to describe every point in detail. Otherwise, you're not going to score good in this one. So they have given us two graphs and they have told us to explain. They told us to explain, not describe. Explain means you have to go into the depths as to why this is happening, not just describe. If I described, I would have said, as the voltage increases, the current also increases, but the rate of current increase is less. That is what I would have said. I would have ended there, but I will not go into the depths of it. That would have been description. But if I want to explain, I would have to go into the depths of it, the reason behind why this is going this way. So for the filament bulb, the gradient decreases with increase in voltage, right? The gradient decreases. The gradient, as we can see, it's decreasing. And the gradient of a I by V graph gives us what? 1 by R. So if 1 by R is the gradient and that is decreasing, that means R is increasing. So why does R increase? This happens because the drift velocity decreases due to greater number of collisions between the electrons. Now, if you are providing more voltage across the filament bulb, each of the electrons are getting more energy. Voltage is basically energy per charge, right? So each of the electrons are getting more energy. If they get more energy, they will strike with each other more. And if they strike with each other more, they will lose velocity because they are, striking with each other, and that results in losing of energy. Right? So the drift velocity decreases, and because I is equal to NAQV, V is the drift velocity. If V decreases, I also decreases, and because I decreases, the resistance increases in the filament bulb. That's the explanation behind this shape. Now for the thermistor, we apply the same method. In the thermistor, we can see the gradient is increasing, and if the gradient is increasing, that means what? 1 by R is increasing. That means R is actually decreasing. If R is decreasing, why does R decrease? The reason behind this is because with the increase of voltage, this happens because both the conduction electrons per meter cube and the drift velocity increase, right? In here, we know for thermistor, it's a negative temperature coefficient device. So that means if you provide more voltage, if you provide more energy, that means more energy provided, that will do what? That will free up more electrons. So if they free up more electrons, not only will they free up more electrons, but also they will move faster. The electrons will not be freed up more, but they will also move faster. So both the drift velocity and the number of conduction electrons per volume increase. So since I is equal to NAQV, because both N and V increase, that's why I also increases. And because I increases, R falls. So that is how we can explain the reason why R is falling in thermistor and why R is increasing in filament bulb. So you have to go into the depths of it, the actual, substantial depths of it, not just describe what you see in the graph. Number 17. The kinetic energy, you have to find the maximum speed of the electrons as they release from the metal surface. So this is a photoelectric effect question. So to find the mass, to find the speed, you of course have to go for the kinetic energy. So the kinetic energy is what? The total energy minus the work function. So work function we can see from here, it's given in electron volts. You convert this to joules, and then total energy is HF. Here the F is not given. Okay, the frequency is not given. So we have to find using the wavelength. So HV by lambda. So from here, 20 nanometer means 10 to the power minus 9. The remaining is as it is. V is of course the speed of light because it's ultraviolet. Ultraviolet it has the same speed as light. Okay. From here, we subtract the work function from the total energy. We're going to get the kinetic energy. But because kinetic energy is half mv square, and out of this, m is the mass of the electron and v is the velocity of the electron. M is the mass of the electron. It's given in the chart, 9.11 10 to the power minus 31. From here, we found v to be this much. Now, our students suggest that if the wavelength and the intensity of light are both increased, a maximum speed of the electrons released from the metal surface also increases. Explain whether it is correct or incorrect. The student is incorrect. Why? Because we know that if the wavelength increases, the frequency will decrease, and if the frequency decreases, E would decrease. The total energy would decrease. If the total energy decreases, that means the kinetic energy would be lesser. Of course, that's what we learned here. The previous one, the total energy is the kinetic energy plus the work function. So if the total energy itself is less, how can the kinetic energy be more, right? So that's why student is incorrect. Also, the intensity has no effect on the kinetic energy. The intensity, as we have learned in the photoelectric effect, it has no effect on the kinetic energy. The only thing that it does, after the emission has started, it simply increases the number of emissions per second. That is all it does. It has no effect on the actual emission to start with. Number 18, plane polarization. Describe how the teacher can demonstrate that the light from the laser pointer is plane polarized. If the light is passed through a Polaroid filter, the intensity only decreases if the filter is rotated. So if you have this light passing through the Polaroid filter, it passes straight through without any decrease of intensity. But if you rotate the Polaroid filter, that means what? That because of the change of plane of polarization, some of the light would get absorbed and the intensity would decrease, and it would become exactly zero if the the polarization plane of the Polaroid filter is exactly 90 degree with the flow of the light. Okay, so that is how we can justify it. State the quantity represented by D. D is basically what? Whenever we write D in the calculations, it is actually what? 1 divided by number of lines per meter. So it's in how many lines are there in 1 meter, right? 1 divided by how many lines there are per meter. So this is basically the spacing between each of the lines, the spacing between each two consecutive lines. So distance between these two lines is one value, is D. This is another D, this is another D, this is another D. Okay, that is how we actually describe it. Then calculate the number of lines per millimeter on the diffraction grating. So we have to use the formula n lambda is equal to d sine theta. So n is the order, and order, as you can see, it's the first order. So the value of n was going to be 1. Lambda is, we know the lambda from here, 532 10 to the power minus 9. We have to find the value of d, and sine theta, the theta value, we have to find from this one, because in here the distance between the grating and the screen is 2.74, and the distance between the central and the first maximum is 1.61. Using tan theta, we can find the value of theta from this one, and that value of theta we put into this one, and from there we found the value of d first. The first value of d that we found was actually in the number of lines per meter. Okay, this was the number of lines per meter, but we need to find the number of lines per millimeter. So whatever value we found, the number of lines per meter, the number of lines per millimeter would be 1000 times lesser than that. Why? Because 1 meter is 1000 millimeters. So if you have whatever number of lines you have in 1 meter, whatever number of lines you have in 1 meter, you will have exactly 1000 times lesser number of lines in 1 millimeter. That's what I did. I divided this by 1000. Then using this diffraction grating, only the first order maximum and the central maximum produced. So you only get the first and the central maximum. Explain how the teacher using the same laser pointer could improve his value for the number of lines per millimeter. So as you can see, n lambda is d sine theta, and they're telling us that the order number doesn't change. It's only the first order that we can go up to, so n doesn't change, right? And because the teacher is using the same laser pointer, the lambda doesn't change, because the lambda is the wavelength of light coming from the laser. That doesn't change. That is also constant. So the only thing that d will depend on is the theta value, right? How can you vary the theta? How can you get a better value for theta to improve the calculation? So distance between the grating and the screen can be increased. So if you increase the distance between the grating and the screen, you're going to get a more spread out pattern. If you increase this distance from 2.74 to let's say 3 or 4 or 5, if you take it far away from the screen, the central maximum fringe would be more spread out. The first order maximum fringe would be more spread out. So if they are more spread out, it's easier to actually measure the distance, because if they're thin, it's difficult to measure the distance. If the fringes are thicker, easier to measure the distance. So that's one way. And the other thing is the distance between the first maxima on one side to the first maximum on the other side can be measured. So if you're just measuring on this side, just this much, 1.61 in, let's say in this case, this might not be a properly accurate value. But if you take the first order maxima here and then you take the other one on the other side, if you take the total distance from here up to here and then you divide by 2, that's going to give you an average value. And whenever we get the average value, that is closer to the accurate, right? So that's what we should do. We shouldn't just take on one side. We should take from here up to the other side, from one first order maximum to the next one. And because they are exactly lying, they are exactly the same distance from the central maximum. So take the total distance between the first here and the first here, divide this by 2, you're going to get the average distance between the central maximum and the first order maximum. That's going to give you a more accurate value. Okay, that's what I wrote. Then number 19, this is a nichrome wire. They're telling us to complete the circuit, and this should include the ammeter, voltmeter, and a variable resistor. So ammeter series, voltmeter in parallel, and variable resistor series as well. and there should be a power supply, of course. So this is the information that we have to use to solve our questions. We have to find the resistivity, which is Ra by L. So the resistance we have to find, of course. Now, which one should we take? There is no specific value. So we have to take any set from this graph. Take any pair of values from this graph of V and length. Okay. So if I wish to find resistance, what do I have to do? I have to divide V by I. And they have told us specifically in the question that the I is constant at 0.2. It's constant. So we simply have to take a value for V from the graph. So let's say I picked the one at the end. I picked the voltage at 1 meter, which came to 4.15 from the graph. So I know the voltage, I know the current is 0.2, which is fixed. So from there I can find the resistance. Once I've found the resistance, I know R. I also know A. How? Because it's given in here. And L is the length at which I found the voltage. I found the voltage at how much? Length 1 meter. So that is what the length is. So makes life easier. This is the resistivity, and it should be an ohm meter. That's the unit of resistivity. Now calculate the power dissipated. Power is voltage into current. So voltage is the voltage at length 0.75. So if you look carefully at length 0.75 in this question, 0.75 is here, and this is exactly corresponding to 3.1 volt on the voltage axis. So 3.1, and the current is fixed at 0.2. That's mentioned in the question. So this is the power dissipated. Number 20, intensity. Long story short, this question is about radio waves being emitted from our power smart meter in our houses, and it's sent to the electricity company to see how much electricity is being used up by the house. To find the intensity, we have to divide the power by the area. So in this question, we have to see if the intensity of the radio waves which are being emitted from the smart meter, if the intensity is safe for people or not. And it will only be safe if it's within 4.5 watts per meter square. If it's more than that, that's dangerous for people. So we simply have to find whether our intensity is less or more than that. So intensity is power by area. Power is given, and the area, it follows the inverse square law. The inverse square law basically is stating that if you and the source, if you are standing here and the source is at the center, the distance between you is R. The source, it will be emitting a power which will be followed uniformly within this spherical region. The sphere's area is what? 4 pi r square. So within this spherical region, the power at all the places, here, all the places within this sphere will be the same. So that is what the inverse square law does. It basically gives you an outline, a border within which the power is the same at all points. So the R is the distance between the source and the person, which is in this case 25 centimeters. So it has to be converted to meters. That's what I did. And then it came to 1.27 watts per meter square. And that is well within 4.5 watts per meter square, meaning this is perfectly safe. Now, next one is finding F, energy per photon. No, you have to find the energy per photon, sorry. Frequency is given. So energy is what? HF. H is Planck's constant, and F is the frequency. The frequency here is given as well. So we found it, and we have to convert this to electron volt. And if you want to convert joules to electron volt, you simply divide by the charge of each electron, which is 1.6 into 10 to the power minus 19. This is the reading of the smart meter, and it shows how much energy is used in one day. It's expressed in kilowatt hour. What does kilowatt hour mean? It means that you are using 1 kilowatt of power every hour. Okay, that's what it means. So here they've told a kettle in the house is a power of this much. It takes this many seconds to heat the water to boil, and then it switches off. So this is the power of the kettle. This is the time it takes. So power is, energy is power into time. Power is 1200 watt. We convert this to kilowatt because that's what we need, kilowatt hour. So this in kilowatts is divided by 1000, and time in seconds, it should be converted to hours. So divided by 3600. This is the energy used up by the kettle. And this, out of the entire day's electricity consumption, is only 0.608%, which shows that it is less than 1% of the total energy. So it's showing that our calculation is correct. Number 21, this is the last question. It's about nodes and antinodes, stationary waves. So frequency of the sound produced by the stationary wave. So this is a first harmonic situation. So first harmonic looks like what? It looks like this, right? It looks like this. So on both sides of the stationary wave, we have nodes, right? So there are two nodes on two sides of the stationary wave, and what's the distance between them? What's the wave, distance in terms of wavelength between them? It's actually half lambda, right? This is half lambda. That's what we know, because this is half of a wave. This is what? This is half of a wave, right? Full of a wave is this much. So this is only half of a wave. So in here, we simply have half of a wave. And if we have half of a wave, that means the distance from the starting place until the ending place is simply half lambda. So half lambda is the distance from one node to the next. Similarly, if the distance from one node to the next is half lambda, the distance from one antinode to the next would also be half lambda, right? So half lambda is the total length of the stationary wave here, right? So the L, the total length of the stationary wave, is simply half lambda. If half lambda is the total length, that means lambda would simply be 2L. So lambda would be twice the length of the recorder. That's what I did. And now that I know lambda, frequency is speed per wavelength. Speed I know. I found the lambda, put it here, I get 699 hertz. Now the musician plays the recorder and produces a frequency of sound as in 1. So 1, we found frequency to be 699. The musician plays the recorder and produces the same sound. The temperature of the air increases, this increases the speed of sound. So if the speed of sound increases because of the increase of temperature, that means what? V equal to F lambda, the V increases. Now they're telling us the frequency has to remain the same. Explain how the musician can adjust recorder to produce the same frequency sound as in 1. So if the frequency has to remain the same, the only way the velocity of the sound can increase is by increase of the wavelength. So how can you increase the wavelength? In just the previous part, we learned that the wavelength can be increased based on the length of the recorder. So if you increase the length of the recorder, the wavelength is going to increase. So that's what I said here, that since the frequency has to remain the same, and as V is equal to F lambda, the increase of V is due to the increase of lambda. To increase lambda, we need to increase the length of the recorder. How can you increase the length? But this is done by loosening up the parts of the recorder. So if you loosen up each of these parts, if you loosen them up, they will become larger. If you tighten them up, they will become smaller, shorter. But if you loosen them up, make them a bit looser, they will be a bit more spread out, meaning the length would increase, and as a result the wavelength would also increase. This is the last part. So on a violin, a stationary wave is created when a string is plucked. When a string is plucked, it produces sound with frequency this much. This string is adjusted to produce a sound of frequency this. So the frequency has increased. So how do you increase the frequency? By increasing the tension. So this is the equation we know. This is the rope wave equation, right? V is equal to T by mu, where T is the tension and mu is the mass per unit length, and V is what? F lambda. So from here, if we take the square root to that side, it becomes F square lambda square, and T is what? F square lambda square into mu. And they're telling us that the length of the string is fixed. If the length is fixed, it means what? That the lambda is fixed, because the lambda depends on the length. So lambda is fixed. Okay. And also they're telling us that the same string is plucked. The same string is plucked. So the string is not changing. If the string is not changing, that means the same string is used. Means what? The mu doesn't change, because mu is mass per unit length. And if the same string is used, that means mass per unit length doesn't change. So mu is constant, and also lambda is constant. So the only thing that the tension depends on is the square of the frequency. That's what I wrote. Now, if I wish to find the ratio between them, so what do? T2 by T1. T2 is the new frequency. T1 is the old frequency. New frequency is 440 hertz, and old frequency is 432 hertz. So the square, of course, the ratio is basically what? T2 by T1 would be equal to F2. Let me just rewrite it here for your convenience. It's going to make a bit more sense. T2 by T1 is equal to F2 by F1. This is square over this, right? That's what we did here, F squared. So this is how we got this one, right? The old by the new, sorry, the new by the old. From here, the ratio came to 55 square, 54 square. So what can we see? We can see that the new tension is 55 square and the old tension was 54 square. So the increase is how much? 55 square minus 54 square divided by what was the original one, 54 square into 100%. So it comes to 3.74. The increase comes to 3.74%. That is the percentage increase of the tension if you increase the frequency from 430 to 440 hertz. Okay, so that's the last question of this paper. Thanks for watching.